present an approach to predict visual attention of elements and automatically place them in a 3D environment while maximizing the overall visual attention received.
Virtual reality headsets like the Fove include eye tracking capabilities. This is very useful in more efficiently designing visual attention experiments. Predicting the gaze duration of an object gives us the ability to quantify visual attention. From that, we can find the optimal placement of objects in a 3D scene that will maximize the total visual attention in that scene. For example, we can find the optimal advertisement placement in a train station, or the optimal placement of artwork in a gallery. Our eye tracking dataset was obtained from users who navigated our virtual environments while wearing the Fove VR headset. We trained a regression model with the eye tracking data. The model essentially learned the relationship between some features of the elements and the visual attention they received. Given a visual element placement in a 3D scene, the trained regressor can predict the gaze duration it's likely to receive. In our optimization step, we automatically place visual elements in the input environment until a total gaze duration target is satisfied. We designed several 3D models based on real-world scenes and placed panels with various sizes throughout them. As users navigate our environment, the gaze duration of each panel they view is recorded. We use features like the length and width of the element, the height, the distance from the nearest light source, the distance from the nearest path, distance from stairs, an occlusion metric, and finally, the distance from the center of the room. By running these visual elements through our regressor, it predicts the following gaze durations. Our optimization maximizes visual attention by adding, deleting, and moving elements across the 3D scene. It halts when it reaches the target gaze duration. We constructed this scene using a level of the Museum of Modern Art in New York City. After running the optimization with a target gaze duration of 25 seconds, these visual elements were selected. In this scene built using the Kenmore subway station in Boston, if we run our optimization with a target gaze duration of 9,000 milliseconds, we get this arrangement of visual elements, with a total gaze duration of 9,029 milliseconds. We can constrain our optimizer to produce a varying number of visual elements. By setting the target duration to 15,000 milliseconds and the prior number of visual elements to 8, we get this placement of visual elements. However, with a prior of 12, our optimization produces the following placement. We presented a novel technique in predicting the attention of 2D visual elements, giving designers the ability to place elements in a virtual environment in a way that maximizes the total visual attention. This is the end of our video. Thank you for watching.